Hello class, this is Ms. Friggins with today's video on section 5.1 Logarithms and Their Properties. As you're watching the video, I cannot stress the importance of writing down notes, especially important vocabulary, formulas, and equations. Feel free to pause or rewind the video or even rewatch the video as needed. And don't forget to write your summary in your notes at the end of the video. After you write your summary in your notes, then submit the online WIS form so that you will be able to get credit for that. All right, let's begin. So we're actually starting something with logarithms. I'm not aware of the extent to which all students learn logarithms in middle school, so I'm just going to start basically from the beginning. If you remember, when we were trying to solve a population problem or some other exponential problem, if we needed if we needed x from a given y, in order to figure that out, we had to either, if it was graphed, we had to look for say for example, y was 4, and we're trying to find which x value makes y 4. And so we see, oh, look, there's an x value here for this graph that makes it 4, here. So then the corresponding x value could be located by making a vertical line from that point. So the y value of 4 is obtained by y equals 4 to x by something close to 1. For something y equals 3 to x, something close to 1 and a 10th. And for y equals 2 to the x, x should be something close to 2, if not 2. And we can find that out via the graph. I want to show you how to do that on the Inspire as well. It's a little bit easier. So let's say I want to do 3 to the power of x. Okay? And then I'm saying, okay, I want to figure out what x value makes the y value 4. Now, of course, I could add a horizontal line, y equals 4, and then I can either find the intersection by doing minimize, analyze, graph, intersection, and they'll want you to look for the area where the intersection is. They want to define that area, and they'll tell you that. Or you could do something that's called trace by hit menu and trace and graph trace. And basically, as you move your arrow button, you can see down to the bottom, it gives you the corresponding x and y coordinate, and you can use that to estimate when x will be, what x value will make y equals 4. But even though this method will work, especially this, it will give you the exact answer, and as close to exact answer as the calculator can give you, it still will be an approximation. It's not the most efficient method. And so we're going to look at a way to determine using the most efficient method. And that is using a function called logarithm. So let's talk about what a logarithm is, so you can have a better understanding. A logarithm is basically a function that was created to show you the relationship between exponents. So whenever I think logarithm, I'm not as familiar with logarithm as I am with exponents, so I can immediately convert the relationship between a logarithm and exponent. So if I have an exponent that's 10 to the something is equal to x, then the logarithm is that something is equal to the log, and this is base 10 of x. So it's very important that you know that log x is the exponent of 10 that gives x, okay? And if you don't understand this one, this relationship is very important. So in essence, logarithms are a type of exponents, okay? So whenever I see a log function, I go ahead, or log relationship, I go ahead in my mind or on paper and change it to an exponential form. So this may be the logarithmic form of the exponent, but this is the exponential form. So let's take a look at an example. So log 4 equals 0.602. I'm going to change that to the exponential form so I'll have a better understanding. So as you can see, y is equal to log of x, so this is my y. So therefore I can say that 10 to the y, which is 0.602, is equal to 4. That's all that means. So let's confirm that using the graph. So let me go ahead and change this to y is equal to 10 to the x instead of 3. And then because I already did the intersection, that was the most recent thing, I get the exact answer. X is 0.602, Y is 4. That's basically by doing window, analyze, graph, intersection, and looking for the area. Okay, so that confirms our answer over here. But let's take a look at something that's kind of interesting. So let me get rid of this. So we already said that this is the same as 10 to the x. So what if I want to graph the log function? If I want to graph the log function, there's a button on here that's right above the 10 to the x button. If I do control and 10 to the x, I'm going to get the log function. Now we are doing the base log, the common log, which is 10. If you don't have to put a number in there, it's going to always leave it as 10. And we're going to say x, because the graphing calculator uses x as the independent axis. And if I graph that, this is what the log function looks like. So what does it seem to be the relationship between the log function and the exponential function? If you indicate they seem to be reflections across the line y equals x, you're absolutely correct. So that would imply that the exponential function and the log function are inverses of one another, and you would be absolutely correct. So we still have this property that holds. So let n be some number. So this property says that log of 10 to the n is equal back to that n. Let's test this out on the graphing calculator. Let me add a calculator page to do this. And let's say log, hit the log button, control 10 to the x, and we're going to leave it blank because we know that. Let's say I'm going to say 100. Log of 100 is equal to 2. Why is that? Well, if you remember, 10 squared is equal to 100. So log base 10 of 100 is equal to 2. If I want to do the same thing to test this out for, let's say, log of 10 to the 19th, oops, made more 10s than I wanted, my answer is going to be 19. So in this case, if this is my x and this is my y, then I would have this is my y and this is my x as well. So in essence, logarithms and exponential functions are inverses of each other only if they share the same base. Here the base of the log function is 10, but here the base of the exponential function is 10. And therefore the power is the answer for each of these. All right, let's take a look at another problem. And over here, if I take the exponent of a log with the same base, then I get the value, the input of the log as the output. So let's try that with this case. Let me do 10 to the, and I'm going to do log. And because they have the same base, I'm going to put 4. And guess what I get out? 4. And I can substitute 4 in for any value. 4.99999, and well, they rounded up to 5, but it's still 4.999 as well. Okay, so that's the property and relationship between logs and exponents. They are inverses of each other as long as they have the same base. The log and the exponent have the same base. Now let's go over some properties of common logarithms regardless of their base, but we're saying here log of x basically has base of 10. But the log of any base, log of 1, is going to be equal to 0, no matter what the base is. And the log of the base number is going to be equal to 1. So let's take a look at that. So control base 10. So if I do base 10 of 0, it's undefined. But if I do control base 10 of 1, I'm going to get it out 0. If I had to change the base to, let's say, 9, I'm still going to get the same answer. No matter what the base is, not 53, I'm still going to get 0. So the log base of any base of 1 is going to be equal to 0, no matter what the base is. So let's take a look at something else. So let's take a look at the log base 10 of 10. So if I use the base and the input of the log as the same number, I get out 1. Let's see what happens if I change the base to 56 and I put in 56. I get out 1. And the reason being is that 56 to the what power gives me 56? Of course, the answer is 1. All right. The second property we already talked about is that the fact that logs and exponents are inverses of each other as long as they have the same base, and that occurs no matter what x is. Now, if you remember when I put in a 0 value for the log, it gave me undefined, and that's because the log, if you remember the graph, the log function has a domain of only positive numbers. If we take a look back over here. So if I ever put a negative number into a log function, it's not going to calculate it because it only has a domain of positive values, even though the range is all numbers. Okay. Third thing is for both a and positive b, just like exponents have some type of properties between multiplying the exponents, so do logarithms. So I suggest you memorize these if you haven't already, because these are very, very important. Okay, and this is the product property of logs, the quotient property of logs, and the power property of logs. Moving on. So let's solve a problem using logs. So here we have an equation that we're trying to figure out what t is. So in all algebra, we have to isolate the t. So first thing first is I'm going to get rid of this 100 by dividing 100 by both sides. So now I get a modified problem of 2 to the t is equal to 3,370,000. I could try and graph this function and find the y value for 3,370,000 and then try and find the x value on the graphing calculator that creates that, or I could use log functions. And the way that we use log functions to solve it is I'm trying to get t by itself, and the way you do that is you apply the log of both sides. So take the log of 2 to the t and take the log of 3,370,000. So if we want to keep the log as base 10, we have to do an extra step. I want to change that to not the log of 10, but the log of 2. And the reason why I want to change it to the log of 2 is because that way I can apply the log function. So I'm going to make this a base of 2. Okay, and we know that if the base and the exponent are the same, then this is exactly t. And then this is whatever log base 2 of 3,370,000 is. So I'm going to go ahead and put my answer, calculate that. So log base 2 of 2,237,000. 1, 2, 3. I hope that was the same number. Oh, see, I already got the wrong number. 3,337,000. Let's see. I always keep forgetting the numbers. 3,370. Okay, sorry, taking up a long time. Okay. Now, the calculator will give you the exact value. So one way that you can do that so you won't get the exact value, but to get the approximate value is instead of before you hit enter, hit the control button and it will give you the approximate value, okay, which is around 21.6. So if we go back over here, the book solved it a little different way by using a property of logs, the power property, but we still get the exact same answer. And this property is called the change of base, but I think the other way, since we have the graphing calculator, is easier. Speaking of bases, if the base is e, then the log is the natural logarithm, and we call that e natural log, or ln. And that's, I don't know why it's not nl, but it's ln. So whenever you see ln, that means the base is e. And we can rewrite the expression as e to the y is equal to x instead of 10 to the y is equal to x. Okay? And certain properties of the natural logarithm same hold because they're still logs. Natural log of 1 is still going to be 0 because remember, it doesn't matter what the base is. The natural log of the log of 1 is always going to be 0. And if the base and the input are the same, then the answer is going to be 1. So since the natural log is a log, then the inverse of the natural log is the natural exponent or natural base. So e to the x and natural log of x are inverses, and they undo one another. And last but not least, these same properties that we talked about on the previous page, power properties, quotient properties, multiplication property, product properties, and power pump. They're the same, no matter if it's the base e or base 10 or whatever base, as long as they all have the same basis. Okay, last but not least, misconceptions and calculator errors involving logs. Log of a plus b is not the same as log a plus log b. And test it in the calculator and you'll see. Log a minus b is not the same as log a minus log b. And log a b is not the same as log a times log b. Okay? And then, of course, log a divided by b is not the same as log a divided by log b. Okay? The only properties that work are the ones that are over here. These are the only properties that we can hold. And they're very similar to the misconceptions, but they're not. Okay? All right. And then, of course, log of 1 over a is not the same as 1 over log a. Okay? So we talked about the properties of logs. And in general, these are the only ones that actually work. Okay? All right, so I think that's about it. I know it's been a long video, but you wanted examples, and people wanted to learn how to use the calculator better, so I had to add some examples for that as well, too. All right, talk to you later.